In this video, we're going to be talking about the double angle identities. In section 5.2 in our text, we described the sum and difference identities, which allowed us to find the sum of a quantity u plus v, the cosine of a quantity u plus v, or the tangent of the quantity u plus v. In this video, we're going to be talking about double angles. Remember, in any sine, cosine, tangent, or any other trig function, whenever we look at the quantity that follows the sine, cosine, or tangent, that trig expression, that this represents an angle. So this 2x in this case is called a double angle, where x is some angle measure, 2x then becomes double its angle measure. So what we're going to be looking at in this section is the sine of 2x, the cosine of 2x, and the tangent of 2x, and determining what different forms those quantities can take. So we're going to be using the sum formulas from the previous section to do that. In this case, we want to think of this 2x as being x plus x. So one way to examine this would be to expand it in that form. Now, from there, what we want to do is use that sum formula that we discovered in the last section and expand this expression. Remember, the sum expansion says you take the sine of the first angle times the cosine of the second angle. So in this case, the sine of the first angle times the cosine of the second angle. We keep the symbol, so in this case, because this is a sum, we keep it a sum. And then we take the sine of the second angle times the cosine of the first. And in this case, whenever we look at that expansion, both terms have a sine x, cosine x in them. When that happens in any other like algebraic sense, if we have x plus x, we understand it to be 2x. If we have uv plus uv, we understand it to be 2uv. In this case, because these are like terms, we can combine those like terms, and it becomes 2 times the sine of x times the cosine of x, which forms the double angle identity for sine. Ultimately, what these formulas do is they allow us to, given a sine x, cosine x, or tangent x value, they allow us to then, using those values, substitute them into the formula to find the sine of the double angle. Now, it's important to note here that the angles are a single x in both the sine and the cosine function, but that this represents a double angle. So we can have this in this simplified expression, sine 2x, or we could expand it into 2 times the sine of x times the cosine of x. All right, let's look at the cosine 2x. There again, we want to think of that 2x as the quantity x plus x. And we'll expand it using the cosine sum formula. Now with the cosine sum, it says you take the cosine of the first angle times the cosine of the second angle. In this case, both angles are x, so that becomes the cosine of x times the cosine of x. You change the sign, so when expanded, this sum becomes a difference. And from that second term, then, we take the sine of the first angle times the sine of the second angle. In this case, they are not like terms. We've got a cosine x times itself minus sine x times itself. But we can do some condensing. For example, cosine x times cosine x we understand to be cosine squared x minus, and then the sine x minus sine x becomes a sine squared x. And that forms one of the cosine 2x formulas. Now you'll notice in this case, when we looked at that cosine double angle, that there's more that we could do with it. For example, here, if we consider the cosine squared, we know from our previous Pythagorean identities that cosine squared is equal to 1 minus sine squared. So we could take this further. One way in which we could do that, change colors here, is to substitute in place of that cosine squared, what if we make that a 1 minus sine squared? And there again, that's coming from those Pythagorean identities. When we do that, then we have some quantities that we can combine. So we have a minus sine squared x and a minus sine squared x, which could be condensed into 1 minus 2 sine squared x. And this forms another variation of the double angle for cosine. So this is also an acceptable form of a double angle for cosine. And that comes from using that Pythagorean identity in this case. Now, we could have, instead of substituting the cosine squared for a 1 minus sine squared, there's another variation we could use. And in this case, that would be, what if I had replaced this sine squared with one of its Pythagorean identities? So let's go back to, it's not the color I want. Let's go back to that cosine 2x that we have there in the green. And in this case, we're going to instead substitute the sine squared as a 1 minus cosine squared. So here we're going to keep this cosine squared minus, now I want to be careful because I'm going to substitute following a minus, so I do want to use parentheses here. I'm going to replace that sine squared with a 1 minus cosine squared. Okay, so next step, it would be then to distribute that minus. In this case, what that's going to produce is a cosine squared x minus 1 plus a cosine squared x. And there again, we've got some terms that we can combine, the two cosine squared x. And along with that, we have this minus 1. So this forms yet another form that the cosine double angle can take on. All three of these for cosine 2x are acceptable variations of the double angle formula because they're all equivalent to one another. In the same manner, in any identity that I'm trying to prove or in any other relationship, each of these quantities that we see on the right side of the relationship could replace one another because there again we've shown that they're all equal to cosine 2x, which indicates they would also be equal to each other. So ultimately, you've got multiple things that we can substitute anytime we're using a cosine 2x. We can substitute one of these quantities, or given one of these quantities, we can replace it with one of the others. And then lastly, we have the tangent of 2x. There again, we're going to treat it much like we did the previous two, and look at it in the form tangent of x plus x. Okay, so the tangent expansion for a sum formula says you take the, it's a fraction, remember, the numerator becomes the tangent of the first angle, in this case, plus the tangent of the second angle. So here our numerator will become the tangent of the first angle plus the tangent of the second angle. And remember that in your tangent expansion, whatever symbol is here in the parentheses is the same symbol that appears in the numerator. Now, in the denominator, we start with 1, and in this case, we're going to switch that sign, so it's going to become a minus tangent of the first angle times the tangent of the second. And there again, we've got terms we can combine. We've also got some products that we can simplify. So in this case, when we combine the two terms in the numerator, we end up with 2 tangent x. And in our denominator, 1 minus tangent squared x. And that forms one variation of the tangent 2x or the tangent double angle formula. It's important to note here that we know from our quotient identities that a tangent function is equal to a sine divided by a cosine, where all three have the same angle applied. So another variation that we can think of in terms of the tangent of 2x is to simply think of it as the sine of 2x over the cosine of 2x. And that would be another acceptable form or an acceptable substitution for a tangent 2x expression. So each of these describe what happens when we have a double angle, an angle plus itself, in terms of how we develop these double angle identities. And it also kind of gives us a use for the sum and difference identities from the previous section.